So in the last class, basically we finished talking about KNN, and we finished implementing KNN in object-oriented fashion, and we tried using KNN for some some basic data set, iris data set. Then we talked about a few evaluations. So we talked about what do you mean by accuracy, what do you mean by precision. We saw how to evaluate precision and recall, and we see that precision and recall give you more insight into how much you're predicting and how you're predicting, uh, at least a little bit more than what accuracy shows us. We also talked about uh, F1 score and F beta score, which are combined scores of precision and recall, so that we can get a single number. We see that F1 score takes equal evaluation or equal consideration to precision and recall, whereas F beta, by depending on what beta we choose, we can control which parameter we want to give more importance to, either precision or recall. We also talked about the threefold split, which is how we take our entire data and how we can use this data to train our model, validate our model, and test our model. Okay. So maybe I can ask you a few questions to just check if you've understood what I was saying. The first question would be, first maybe, what is the purpose of evaluation? Why do I need to evaluate the model?
To understand the accuracy of the model.
Okay. Why do we want to understand the accuracy of the model?
Then only we can go with other variables and we can predict.
Okay. Okay. Yeah. So maybe a key concept here is we are interested to use this model over unseen data. Okay. So the data that we have presently with us is we know the answers for that, or the hope, at least in entire supervised learning, the understanding is that we have labeled data. So we know what the answers are, and we're creating this model so that when we get unseen data, a similar kind of unseen data, how will our model perform? Okay. So to know how good or bad we did, we need to have an evaluation. So for that, we will evaluate our model. Okay. So can you also tell me why these three splits and what is the purpose of each split?
First set is for training. In Canon, we just save it. Validation set is to get that K value. And third is for prediction and checking whether it is correct or not.
Mm-hmm. Okay, that's right. We'll divide into training, validation, and test. Training, as he said, for KNN, it does not make a lot of sense. But now, as we move to other algorithms, you will know why or what we are training or what we are trying to fit or what we are trying to learn from the training set. Validation set, as he rightly pointed, for KNN, it is choosing the value of K. Now, remember this part, or at least pay special attention to what validation set is doing. We are doing something called as parameter selection, which last time I renamed it to, instead of parameter, I'm calling it hyperparameters. And for training set, whatever we are fitting, let's call those parameters. Okay. So what is the difference between parameters and hyperparameters is something that we need to get more clarity on as we go towards your other algorithms and see how things work out. Now, in this method of threefold split, we take the entire data, divide into three splits: training, validation, and test set. The pro is that this is a fast and simple method. The con is there is high variance and bad use of data. When I say bad use of data, we will say, let's say your validation, in this case, if you are not, what do you say, if you have less data, first, if you have less data, then in this case, you're getting to train your model only with a small part of your data, only with a small part of your data. And because of which your model may not be able to capture the patterns. So the whole game of machine learning and data analysis talks about I need to have enough data to be able to train the model. The model should have enough data to be able to learn the system well. Okay. And with this method, I don't get enough data, at least depending upon how much data I have. For less data, this would, your training would be trained by a very small component of your data, because of which your training may or may not be successful. Okay? We'll talk about some more problems here in this in the coming slides. In contrast to that, we have something called as cross validation. And in cross validation, we will use our entire training plus validation data to train the model. So we take our entire training plus validation and we split them into multiple parts. So in this case, we are splitting them into 5 parts. Each part is called a fold. So they're called 5-fold validation or 5-fold cross validation. In this 5 parts, what we'll do is we'll evaluate our model, or we will train our model multiple times. For 5-fold validation, we will be evaluating it into 5 different times. Okay? And each time we evaluate, we will use a different fold for validation. Each time we evaluate, we use a different fold for evaluation. So the advantage is your model gets to see all of your training plus validation data at least one time in its training history. Okay. Additionally, you will get 5 evaluations of the model. Okay, your model will first be trained by this model. You're trained by this data, evaluated on this, trained on this data, evaluated on this, trained on this, and evaluated on this, and so on. You will get 5 different evaluations and 5 different trainings, because of which your results, that is how good a model is or how good are my hyperparameters, becomes more stable. Okay. Additionally, you get more of the data. So what do I mean by more of the data? We will look into that just ahead. Okay. One con could be that this is slower. Okay. The reason it is slower is because you have to run 5-fold evaluation. You have to run this iterations 5 number of times. For 10-fold evaluation, it will be 10 number of times, and so on. So as you go on increasing the number of folds, your model will take more time for cross validation. So the idea between this is something like this. I take all of my data and I divide all of my data into 2 parts, training data and test data. Okay. Once I have the training data, I can go ahead and divide them into folds. Okay, so here we are dividing into 5 folds. Fold 1, 2, 3, 4, 5. Since we have 5 folds, we will be training, or we'll go with multiple iterations, 5 iterations. Okay. And for each iteration, we will use a different fold for our evaluation. And the purpose of all of this is to be able to find parameters. These parameters are multifold. You are also trying to find parameters plus hyperparameters. Okay. Once with all of this, you have trained your model. So finding parameters is basically training your model. Once you have trained your model, you will then use that model to evaluate on the remaining test data, and you'll get the answer of that. Okay. So this would be the strategy for dividing it into cross validation. It's the same image. I think I duplicated a PPT slide, but I forgot to delete it. Anyway, let's go ahead. Now, sometimes there can be a problem like this. Okay, if I do standard class validation with sorted class labels. Okay? So if we have as our data, we have used KNN, right? For KNN, we have used iris data as an example. And if you observe on iris data, initially you get the labels in sorted. So you have all class 0, then followed by all class 1, followed by all class 2. So they are sorted labels. If I take a sorted labeled class, okay, and within that sorted labeled class, if I try to take the divide into 3, so like let's say you're dealing with your iris dataset, which has 150 examples. The first 50 examples belong to class 0. Okay, so it is already here. The first 50 examples belongs to class 0. The next 50 examples belong to class 1. The next 50 examples belongs to class 2. So we will, since we have 3 folds, we will have to do 3 iterations. In the first iteration, we will use this data to train, class 1 and class 2 data to train, and test on class 0. Okay, how good do you think the evaluation will go? If I train with class 1 and class 2 and I evaluate on class 0, will the training be good?
No.
No, right? Because our first assumption in machine learning training is we said that the test data should be, the training data should be a representative of the test environment. And if we cannot guarantee that, or if we cannot, if that assumption is failed a lot, then our training will not be good. Our evaluation will show very poorly. So similarly, for this, what happened here is happening in the next case also. We are using class 0 and class 2 to train for class 1. So very bad approach. And then we are using class 1 and class 0 and class 1 to train for class 2. Again, a bad approach. So if I have sorted tables, I can have this kind of problem, for which we will have to move to a different kind of cross validation, or at least one more criteria within the cross validation. The criteria within the cross validation is, when I have multiple classes, I want each of my folds to have equal representation of the three classes. Okay, so consider the same example here of iris data set, 50 points, next 50 points, and next 50 points. In the first 50 points, we take one third of it. We take one third of this point as our validation. In the next 50 points, I take one third, the first one third for our validation, and the next 50 points, the first one third of our validation. In that case, we have within the first split for training, we have equal representation from each of the three classes. Okay. So we will use this 3 as our training data, and we'll use these 3 as our validation data. So since we have equal representation, this situation is much better than this situation. We do similar case for split 1, split 2, and split 3. Okay, and this method is called as stratified cross validation. So if you remember, when we were using train test split within our KNN, even within our KNN, I specified an option called as stratify equal to y. Okay, do you remember that?
Yes.
Okay, and we saw that after doing that, we saw that the values of or the class labels within the train set, the validation set, and the test set were then equally split. Okay, so we can do something like this from scikit-learn itself. Okay, so we can specify which variable you want to stratify, and what it means by stratifying is having equal representation in the split, so that we get our good training, validation, and evaluation. So I hope you have got that part right. Do you have any questions before we move ahead? Okay. So let's move to the next topic. We will look at another important classifier. We're looking at naive-based classifier, and we'll see how it works and what is the theory behind its functioning. So we have already seen KNN. So what I would request you to do is, as we are going through this naive base, just try to compare within your mind how KNN is working and how naive base is working, and what advantage would be there to work with KNN, what advantage would be there to work with naive base, and similarly, what will be the cons for KNN and naive base. Okay, so let's focus on naive base for now. So as you see, the naive base classifier, it works on the Bayes theorem. Okay, uh, I hope you must have gone through the Bayes theorem within your probability class, maybe in 11, 12, or later on. Okay. Anyways, we'll do a small revision on what the Bayes theorem is, and we'll see how we can use it for classification, okay, or for data analysis, machine learning. The naive term comes because of the naive assumption that features are mutually exclusive. That is, they have no correlation between them. And we will discuss a little bit more on why it is called naive, and what is the use of this assumption, and what is the drawback of this assumption. Okay, the assumption is that when I have multiple features, that these features are not correlated with each other. So like for example, mm, think of a good example. Okay, so we looked at a Titanic data set, and in Titanic data set, let's say there are two columns, one for class, passenger class, P class, and the other for fare. Okay, the fare of the fare that took, for what is the ticket price. Okay. Now, when you look at these two columns, we know that there is some correlation between them. Okay. We have three classes. We understand that uh, class 0, 1, and 2, class 1, 2, and 3. Class 1 would be costlier than class 2, which would further be costlier than class 3. Okay. So we know that there is an inherent relationship between between the passenger class and its fare. What naive Bayes will do is it will ignore this assumption. It will say that, okay, I don't really care if there is a correlation between fare and P class. It will consider them as different identities. Okay, and the loss of that is if you do something like that, you may have wrong probability, or uh, you may have biased probability towards one class, towards one label compared to the other label. And this bias may actually help us, or this bias may actually destroy our generality, which means that for unseen cases, we may not have very good results. So we'll look into more of this as we go deeper into the example. Further, we see that naive Bayes is very easy to build. So as soon as we look at the idea of how it is working, you would understand that it is not very complicated, or we would require a lot less programming to be able to build naive Bayes. Okay. Uh, Additionally, it is very, very useful for large data sets. Again, so once we see how it's working, we can probably guess why it is useful for large data sets. Let me go deeper inside, and we'll first quickly summarize, or we'll see how does Bayes theorem work. So have you looked at this kind of a symbol before? Can you tell me what does this symbol represent? You have not looked at the symbol, Anand?
I don't remember.
Okay, you don't remember. Yeah. Srinivas, are you saying something?
Yeah, is it probability?
Yes, yes. P of something shows probability. And within this, can you also tell me what does this bar stands for?
Is it mod?
What did you say?
Mod?
Mod. No,
Mod.
no, 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 not mod. Mod is, yeah, I think 2 bars is mod. So this would be mod of x. Okay. So yeah, I'll tell you. Switcha, do you have an answer for this?
Probability of A when B is true.
Yes. Probability of A when B has already happened. Okay. So within probability, you may remember that we talk something called as events. Okay. And events is something that happens. Event is how we define things. So let's say if you're tossing a coin, you can say the act of tossing a coin could be event A. Okay. And if you say after shuffling a card, if I remove one card out of the deck of 52, that could be event B. Okay. Here, probability is read as probability of A given B. Okay, or it would be read as the conditional probability of A such that B has already happened. Okay, so that is what we mean by A and this given B. Okay, so here we are reading, or Bayes theorem says that the probability of event A happening such that event B has already happened is equal to the probability of event B happening such that event A has already happened multiplied by probability of A divided by probability of B. Okay, so here we see two kinds of terms, something called as prior probabilities. Prior probabilities are these terms here, where these probabilities A and B, they do not depend upon anything. Okay. So probability of A would be you take event A and you find all the examples in the sample space. Out of all those examples in the sample space, you see how many of them have become true. Okay. and the number of truths divided by all the sample space would give you the probability of A. Similarly, however you evaluate probability of B, you will have to do something similar. Okay, these events A and B are having no relation, or even if they have relation, probability of A and probability of B have no relation between them. Okay, and so we have pair probabilities and we have conditional probabilities. Conditional probabilities are probability of something given something else has already happened. Okay. So the interesting question is, how is Bayes' theorem used for classification? How can we use that? Okay. Maybe a small note for Anand. You may remember we were using for the Airbus project, we were using Bayesian analysis, right? For
Yeah, health analysis for health.
yes, for prognostic health. So we had uh, our different aerospace systems broken down till the smallest level. And when we look at what will happen in the smallest level, we can probably guess
Okay.
what is the prognostic health of some of the entire system. Right? So
Yeah,
I forgot the name of the software, but we were using the theory behind the software was using Bayesian theory.
yes.
Anyways, let's go ahead. Uh, we are asking the question now, how can we use Bayesian theorem for classification? Okay, or how does naive Bayes work? So let's understand, or let's revise how our data would look like. So we would say that let D be the training set of tuples. This is the training data that we have. Okay, so for for this entire training set, we have several examples: x1, x2, x3, x4 till xx. Each example or each sample is further represented by an n-dimensional attribute vector. So x1 can be made up of smaller x1, x2, x3 till x till xn. Okay. So just imagine, let's say we are talking about our Titanic data set. X1 would mean one entire row. Okay. Within that entire row, I have age, fare, ticket price, gender, sibling, spouse, parent, children, and so on. So these would be your individual x1, smaller x1, x2, x3 till xn. And this would be each row. So x1 would be row 1, x2 would be row 2, x3 would be row 3, and so on till we have x samples maybe. Okay. So that is what terminology that we're using. Training set D and training tuples x1, x2, x3 capital, and then within those training tuples are different attributes. Now let there be m classes. Okay, m classes is how are we going to categorize this? So since we are talking about supervised learning, within supervised learning we're talking about classification. We have fixed number of classes. For our Titanic data sets, we have only C1 and C2. C1 showing that a person has not survived, and C2 showing the person has survived. Okay. So for our Iris dataset, we had three classes, C1, C2, C3. C1 showing class 0, which is maybe the three different classes, uh, versicolor, virginica, and cetrosa. Okay, so we have 1, 2, 3. So that would be our M. Now, for our prediction, we will use this term. Okay, we'll say, what is the probability of Ci given a particular sample X? And what is the probability of Cj given a particular example X? And we will run this, we will evaluate this, we'll evaluate this inequality for different values of I and different values of j. So I and j will go through the entire range from 0 to m such that I is not equal to j. Okay. So let's say if you're going for, if you're trying to do this for our Titanic data set, we would say that what Ci would, let's say C will have two classes only, 1 and 2. We will have to evaluate probability of, we'll have to evaluate probability of class 1 given X, and we'll have to evaluate probability of class 2 given X. And depending upon which is greater, let's say this one is greater, we will say that then we will name our target as class 1. If this one is greater, we will name our target as class 2. Okay. If you're doing this for your Iris dataset example, we have m is equal to 2. So it will go from 0, class 0, class 1 and class 2. In that case, we'll have to evaluate all three probabilities and we'll have to see which one is greater. Okay, whichever is greater will be the answer that we will be giving. Okay. I hope this is clear so far. Okay. Okay. So now we'll see how do we evaluate this part. So what is the probability that a passenger has survived given the data that we have, given the different attributes that we have? And what is the probability that the passenger is not survived given the attributes that we have? So Bayes' theorem says that to evaluate this, what is the probability of a particular class given the attributes we have, can be done using this formula. It says, what is the probability of having a given feature given that we already know the class of from the data. Okay, so let me read this again. This is very interesting. It is saying, what is the probability that we have a certain feature if we already know the class of the variable, the class of the sample? Okay, so that multiplied by the probability of the class happening divided by the probability of the sample happening. Okay, we'll read this again. The probability, what is the probability that this data belongs to a particular class? Okay. Bayesian theorem says that the probability that this data belongs to a particular class is equal to the probability of that data given that we know the class multiplied by the probability of the class divided by the probability of the sample. Okay. Now we'll have to compare or we'll have to evaluate this formula for all the different classes that we have, right? So let's say if you're doing it for your Titanic data set, we have again two classes, 1 and 2. So we'll evaluate this term for what is the probability of this event happening. What is the probability that the passenger has not survived given this data? So we'll say, okay, I will evaluate this. What is the probability of getting this sample given that the passenger has not survived? What is the probability of the of not surviving in general? And what is the probability of this sample? So since we have to evaluate this, let me write it out in such a way. We have to evaluate if probability of class C1 of X is greater than probability of class C2 given X. Or in other terms, we have to evaluate probability of X given C1 multiplied by probability of C1 divided by probability of X. And we have to check if this is greater than probability of X given C2 multiplied by probability of C2 divided by probability of X. Okay. Now within these two formulas, can you tell me one term that I do not need to evaluate and still I'll have the same answer? Are you saying? Yeah, yes, Svecha. I could not hear you, Svecha. Can you say that again?
Probability of X.
Yes, excellent. So within this formula or within this evaluation, if I don't evaluate probability of X, I will still have the same answer, right? I can simply cancel this out because I have the same terms on both sides. Even if I don't evaluate this, I can still find out the relation between the first formula and the second formula. Okay, so excellent. Now the question is, okay, how do I evaluate? So maybe can you tell me how can we evaluate probability of a class happening? So in our specific example, what is the probability that someone did not survive, and what is the probability that someone survived?
So probability of a person survived by total number of persons.
Okay. No, you're saying what is the probability of a person survived? That is probability of the. How do you evaluate this?
That probability will be the number of persons survived divided by the total number of persons.
Exactly. From the which data?
From the test data.
No, we don't have access to the test data, right?
Oh yeah.
Training data.
Yes, from the training data. Excellent. So we'll take our training data, and from our training data, let's say we have, for our Titanic data set, we have 891 examples of training data. And for all those 891 examples, we know the class, when the person has not survived, when the person has survived. When the person has not survived, we'll just count from 891, how many people have survived, how many people have not survived, divided by total 891. And that would be our this probability. And 1 minus this would be at this probability, because this is anyways binary classes, right? One or the other. If you're looking for SecA, then, or if you're looking for Irish data set, then this probability would be, what is the probability of how many class 0 we have divided by total, how many class 1 we have divided by total, how many class 2 we have divided by total, and we can easily evaluate prior probabilities. Okay. The more interesting question is, how do I evaluate this thing? Okay. So if I say that, okay, let me use Bayes theorem again to evaluate this thing, then we are beating around the bush, because we don't have this part. Okay. So we'll have to find some other way of evaluating this part. What is this part? What is the probability of getting certain features given we know its class? Okay. And this is where we use a formula like this, where we say that the probability of getting a certain feature or getting a certain sample, given that we know the class, is given by, do you know what this symbol stands for? Anyone? Have you seen this symbol before? Okay. Anand?
For loop.
For loop?
Just from the k equal to 1 to n, that from that I get.
Okay, from kids. Have you seen this symbol before?
Summation here.
Yeah. So you have not seen this one before, huh? I'm surprised.
No.
Okay, this is the product symbol. It's pi. So summation symbol, when you say k is equal to 1 to n of xk, this was the answer would be x1 plus x2 plus x3 till we go to xn. Okay, and if you're talking about the same thing with respect to pi, you'll say x1 multiplied by x2 multiplied by x3 multiplied by x4 till multiplied by xn. Okay, this basically says product of all values within the operator, all values within the operator, as k goes from 1 to n. So in our case, this would mean that this would be evaluated as probability of small x1 given ci multiplied by probability of small x2 given ci multiplied by probability of x3 given ci, and then dot 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 probability of xn given ci. Okay. So here we are saying that to evaluate a certain probability, to evaluate this kind of probability, we are saying that this probability is made by multiplication of the individual probabilities. Okay. And do you know when we can multiply probabilities together? So let's say if I give you the probability of tossing one coin and getting a heads is 1 by 2, right? If I say what is the probability that I toss one coin, get a heads, then again toss that coin and get a heads, what is it? What is its probability?
I didn't get it.
Okay, so if I toss two coins, what is the probability that I get both heads?
1 by 4.
Yes, and how did you evaluate that?
First, okay, 1 by 2 multiply with 1 by 2. Yeah, we'll get 1 by 4.
Yes, you did 1 by 2 multiplied by 1 by 2. Okay, and why did you multiply them together? Why did you not add them or do something else with it?
That makes sense.
Okay. Yeah, the sense you're talking about is called mutually exclusive events. Okay, that is the first coin tossing has nothing to do with the second coin tossing, And because of that, I can simply choose to multiply the two answers. Okay. Let me change the scenario. Let's say you have 10 cards. Okay. 10 different cards. Let's say their 10 cards are named from 1 to 10. Okay. And I ask you, what is the probability that in the first draw, in the first taking one of these cards, I pick out the card number 3. Okay. Can you tell the answer for this?
1 by 10.
You'll say 1 by 10. Excellent. Okay. Then I'll ask you, now after this, after I have removed 3 out, I have 9 cards. What is the probability that now I remove the card 2?
1 by 9.
1 by 9. Excellent. Okay. So now we see what has happened is the first event has affected the second event, right? Had I said something like this, what is the probability that I remove the first card as 3 and even the second card as 3? Your answer would have been 1 by 10 multiplied by 0, because the second card can never be 3 because the first card you have already removed outside, right? So now this is an example of events which are not mutually exclusive. Okay. And when events are not mutually exclusive, then I cannot evaluate them by multiplying them together. Okay. So if the event was, what is the probability in the first case? What is the probability that I draw a 2? You would say 1 by 10. But if I say that what is the probability that I draw a 2 after removing one card already, the answer is 1 by 9. Okay. And because of this kind of a scenario, when the events are not exclusive, I cannot multiply them together and get the answer. Okay. Whereas here you see we are doing that. It's saying that what is the probability of a given feature when we know the class. We're saying, okay, the probability is the product of the individual features when we know the class. Okay. That is, what is the probability that someone survived given, what is the probability that this is the age given we know someone survived? What is the probability that this is the class, passenger class, given we know someone survived? What is the probability of this is the fare given we know someone survived? Okay. I hope this makes sense. If this does not make a lot of sense so far, we'll look at an example and hopefully that will make more sense. Okay. Before going to that example, do you have any questions?
Bayes theorem and Bayesian network, both it is almost same.
Yeah, Bayesian network would mean you consider a network and then you evaluate the values of those network using Bayesian theorem.
Okay.
Okay, so Bayesian network would be an application of Bayes theorem.
Okay, fine.
Okay. Yeah, let me go to the example. Probably the example will make some more sense on how things are happening. Okay. So let me focus on this part. So let's say if this is our data, this is our training data. We have 8 examples of training, and this is our test data. And we want to, using this training example, we have to learn something that will help us to evaluate for this unseen case. Okay. What is our example? Here, this is a medical example where we are looking for certain base features, like does someone have the chills? Does someone have a runny nose? Does someone have a headache? Do they have a fever? Okay. And based on this information, we are seeing does a person have flu or not. Okay. Now for the past 8 examples, we have data. So let's say, for example, someone has chills and they don't have a runny nose and their headache is mild and they have fever. Then we say, no, they don't have flu. Okay. Here's second example. You say someone has chills, someone has a running nose, does not have headache, does not have fever, then they have flu. Okay. So you see what these training samples are trying to do is they're trying to explain to us what is the underlying system. Okay. And the training examples gives us eyes into what is happening with the system. And we are not interested in individual training examples. We are interested in understanding what that system is. Because if you understand that system, then you can go to an unseen case like this. It will, someone says, if they have chills, if they don't have runny nose, if they have a mild headache, And if they do not have fever, what is the answer? Okay. So these data are eyes for us to see into what is happening inside the system. And once we understand the system, we will be able to predict for an unseen case. Within our base theorem or naive Bayes criteria, what we are going for is, what is the probability of someone having the flu? That is, flu is equal to yes, given a certain X, given a certain combination of this data. Okay. And we are saying what is, and further we are trying to evaluate what is the probability of someone not having flu, someone not having flu given the same X. Okay. Once we evaluate these two probabilities, whichever is greater or lesser, based on that we will decide the sample. Okay. Now what Bayes theorem says is to evaluate this part, to evaluate probability of having flu given X is equal to the probability of X happening given we know that flu has already happened, multiplied by probability of flu happening. Multiplied by probability of flu is equal to yes. No, iPad is giving some trouble. Okay. So this is what we need to evaluate. Okay. For this evaluation, I am using this table next to me, and we'll see how this works out. So first question, what is the probability of having flu? Okay. So what is the probability of having flu? You go to our 8 examples and you count how many of them have flu. So we have 1, 2, 3, 4, 5. Out of 8 examples, we have 5 examples of having flu. So I say, okay, probability of having flu is 5 by 8. Thereby, probability of not having flu is 3 by 8. Okay. So far, things are clear, right? Okay, excellent. Let's go to the next level now. Now we are taking one of the features. So we are looking at chills and we are trying to evaluate two probabilities. What is the probability that someone has the chills given we know that they already have flu? And what is the probability that someone does not have chills given we know that they already have flu? Okay. So how many examples do we have of a person having flu? We have 5 examples. Out of those 5 examples, 1, 2, 3, 4, 5. For chills, how many cases do we have chills? So we have 1, 2, and 3. Okay. Out of the 5 cases that have flu, we have 3 examples where the person also has chills. So the probability that someone has chills, given that they already have flu, is 3 by 5. Okay. Still makes sense, right? And probability of someone does not have chills, given that they have flu, is, look at this example and this example. They have no here, which is 2 by 5. So here we are trying to evaluate what is the probability of someone having chills given they have flu. What is the probability of someone not having chills given they have flu? So we have 3 by 5, 2 by 5. Let's look at one more example. Maybe look at this part. What is the probability of HA? HA is headache. What is the probability of headache given that we know they do not have flu? So do not have flu, we have 3 examples, 1, 2, and 3. And headache has 3 options, mild, no, and strong. Okay. So first look for mild. Okay. So mild has 1 example out of 3. So we'll say the probability that someone has mild headache, given that we know they do not have flu, is 1 by 3. So what is the probability that someone has no headache, given that we know they do not have flu, is again 1 by 3. Probability that someone has strong headache, given that we know that they do not have flu, is 1 by 3 again. Okay. So do I need to go through more of the examples, or have you understood the pattern of how we are creating this table? Do you get how we are creating this table?
Yes, yes.
Okay, excellent. So once we have created this table, that is, we have both our prior probabilities. So how many prior probabilities we'll have? We'll have as many prior probabilities as there are classes. And then our conditional probabilities. So how many conditional probabilities we'll have? we'll have as many conditional classes depending upon the features and the options that they can take. So chills is one feature, it can take yes and no. So within yes, it will have two examples, two probabilities. Within no, it will have two probabilities. If we have a feature which takes three different values, so like headache takes mild, no, and strong, then for that feature, we'll have three different conditional probabilities for yes and three different conditional probabilities for no, and so on. So like this, we'll have to evaluate how many conditional probabilities we have and how many prior probabilities we have. Once we have evaluated these terms, we are asking the question for this unseen data. Okay, so we're asking the question: what is the probability that someone has flu given we know the data? And what is the probability someone does not have flu given we know the data? Okay, so you say, okay, for the first case, probability that someone has flu given this data is, let us evaluate what the data is. Okay, so here we will have to say this would mean probability of chills is equal to yes given they have flu. So I'm not writing the flu part. Let me write. Given they have flu, multiplied by the probability of, what is this? Runny nose. Probability of runny nose is equal to no, given that they have flus, multiplied by probability of headache is equal to mild, given that they have flu, multiplied by probability of fever is equal to no, given they have flu, multiplied by the probability of flu being yes. Okay, so this would be a numerator, right? We'll evaluate this for yes, that is someone having flu, and then we'll evaluate the same thing for no, for someone not having flu. Okay. Now, in our first case, probability of chills, yes, given yes. So we are going for this one. 3 by 5 is 0.6. Runny nose no, given yes. So yes, runny nose no is 1 by 5, which is 0.2. Mild headache given yes. So HA, mild headache given yes, 2 by 5, which is, okay, did I do something wrong? 2 by 5, which is, yeah, 0.4. Great, 2.5 is 0.4. Okay. Probability of having no fever given yes. So no fever given yes, again 0.2. Probability of having flu, 5 by 8, which is 0.625. So multiplying all this together gives us 0.006. Okay, so great. Does someone have flu? No, we cannot find out now. We have to find the other example also. So we'll find probability of not having flu given this data. Same as we generated here. You replace, instead of y, you replace n. So chills, yes, no. So having chills but not having flu is 1 by 3, which gives you a 0.33. Okay. So you run through this example, you will have all these numbers. When you multiply all these numbers, we end up with 0.00178. Okay. So does this person have, so for this unseen data, what do we predict? Do we predict that they have flu or not flu? What is the answer?
Not true.
Not flu. Excellent. Why? Because this probability is higher compared to this probability. Now this probability may not be true probability. Why? Because we have not used Bayes' theorem exactly. True probability would mean this divided by the probability of this x happening. Okay. Again, the probability of this x happening is very difficult to evaluate. Or it's not very difficult actually. You have to see all different examples of what things can happen. So here you'll have 2 multiplied by 2 multiplied by 3 multiplied by 2, which is 8, 10, 3, 24. So this could be 1 by 24. So this divided by 1 by 24 would give you the actual probability according to Bayes' theorem for this data. Okay. But since we'll be dividing both these cases, it doesn't matter. So we have skipped that part. And now we have this example. Okay. Great. Do you have any questions on naive Bayes? Okay. It's a very genius example, right? In the sense of how someone, so I am 100% sure that when Bayes, he created Bayes' theorem, he would have never thought that someone someday would be able to use Bayes theorem for doing a classification machine learning problem. Anyways, yeah. So can you tell me what are the advantages of this system? So now, as I said, to compare in your minds, KNN and naive Bayes, can you point out what could be the advantages of naive Bayes over KNN?
Even if the test data has less, it will be able to predict better.
And why will KNN not be able to predict better when test data is less?
Because we need to find K. That's a problem.
Okay. You can find K with one data also. You can just try different values of K and you can see which K did give us best. So we will have, of course, you will have a validation data set. Here also you will have a validation data set. Do you understand what I'm saying?
Yeah, got it, got it.
In both cases, you will have validation data set. You need to have validation data set, okay, to be able to judge if you're doing well or not. But even with one example, we can find the value of K. That value of K may not be best. It would be biased because of that one example and the location of that example. But you would still be able to evaluate it. Okay. Any other advantages that naive Bayes would have over KNN? So, yeah, go on, Swesha.
I guess when we have taken this non-uniform data example, like a patient having cancer or not, then we said that taking this K value on KNN will fail.
No,
But
no. For unbalanced set, what I said was accuracy as a metric would fail,
yes,
but not necessarily KNN would fail.
okay.
So one thing that could help us to evaluate if what is the difference between naive Bayes and KNN is think that if you have this data and you have this unknown data, how would you do that with KNN? We have already seen how would we do that with naive Bayes. Okay, can you think of how would this example be solved with KNN?
Why not? Because why all this thing we will convert to a number and we can train and we will be able to predict, right?
Right. How will you predict it? But you will take the first sample. Then what you'll do with this sample, you will try to find the distance between this sample and 1. You'll find the distance between this sample and 2, this sample and 3, and so on. Right?
It won't be there.
What?
That same condition won't come in our test data.
No, that's okay. We're not talking about the condition. We're just talking about distances, right? This would you will code y and n as 0, 1. You would code mild and mild
0,
more
1,
strong
3,
as 0, 1, 2.
0, 1, 2.
Okay, and fever as yn. So we can evaluate the distance, right? So you'll evaluate distance between this and this, this and this, this and this, so on. After evaluating all 8 distances, you will find out, let's say you have chosen, somehow you have chosen the value of k as 3. You will find out which are the closest 3 neighbors. And for those 3 neighbors, you will verify what is their final target. And based on that target, you will predict for test. So of course you can use KNN here. My question is not if you can use or not. My question is, what is the difference or what is the advantage of naive Bayes over KNN, or what is the advantage of KNN over naive Bayes? So let me give you something more interesting. Okay. So instead of these 8 examples, if I have 1,000 examples, then what will happen?
I didn't get it.
For 8 examples, you've understood what will happen, right?
Yes.
If we have 1,000 examples, so let me give you some metrics over which you can measure. Okay, is naive Bayes faster or is KNN faster?
Naive Bayes is faster.
Okay, why?
Because okay, it's just multiplication of numbers.
And in KNN, it is just distance between two numbers. No?
Okay.
So your answer is right. Naive Bayes is faster than KNN. Excellent. But my question is, why is Naive Bayes faster than KNN?
Maybe we need to calculate the distance between each and every test point and the train.
Excellent. So KNN, we have to evaluate distance between each and every test point. But Naive Bayes, why will Naive Bayes take less time? Because here also I have to use each and every example, right?
Once we have calculated the probability of individual, that remains the same throughout.
Yes, excellent. So you see, to evaluate for these probabilities for Naive Bayes, I do not need test data. I'm evaluating these probabilities using only the training data. Okay. So my training phase will be longer than KNN, because KNN there is actually no training phase. You're just remembering the data, and how much time it takes to transfer from one place to the other is the training time that KNN will take. The training time for Naive Bayes would be little longer because you're evaluating all these different probabilities. Okay, but once you've evaluated these probabilities, when you're using when you're using Naive Bayes, you just have to multiply this once. Okay, look at the relevant feature that your unseen data has. You already have a table of these probabilities. Put them into this formula. Evaluate this. Okay, so here you will have to do 1, 2, 3, 4, 5 multiplications for getting one answer. Whereas if you have 1000 rows for KNN, you will have to take your test data and evaluate these 1000 distances between all those 1000 training samples. Right? So you do that for test sample 1. After you have done for 1, you have another test sample. You have to do this entire exercise again. Okay. So KNN will have a very long run time. So for prediction, KNN will take a lot of time, whereas Naive Bayes will take much lesser time. Does it make sense? Okay.
Yes.
Okay, let me give you one more example. Okay, let's say you have this algorithm, and you are deploying that algorithm on a smartwatch. Okay, so you have a smartwatch to which you can the smartwatch will ask you questions like, does a person have chills, runny nose, headache, flu, and you will answer by voice. Okay, once you have answered by voice, it has to give the prediction whether you have flu or not. Okay, so can you deploy KNN on smartwatch?
No, its runtime is more.
Yes, one thing is its runtime is more. Second thing is you will have to load all of the training data on the smartwatch. So if you have, let's say, 1 million examples, all those 1 million examples would have to go into the smartwatch. Whereas for Naive Bayes, you would, on a prior data set, you will evaluate these probabilities, and only these numbers have to go to the smartwatch. Does that make sense? So if your deploying environment has less memory, then KNN will not work out. Because KNN...
Wait. This Canon also, if the test data here we are loading is less, in Canon also with less test data it can run that, but accuracy won't be less, will be less.
No, with KNN, you need the entire training data on the deployment environment, because you have to evaluate the neighbors.
Yeah.
So with the test data, you will have to evaluate the distance with each of those neighbors.
Okay, here we have an intermittent thing.
Here we just need these numbers, probabilities. Okay, so here we have how many examples? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 20 numbers that needs to go onto your smartwatch. And here you have 1000 cases that will have to go to the smartwatch. 1000 cases, and each of those cases having 5 features or 6 features. Okay. So Naive Bayes will take less space on the deployment environment. It will take less time on the deployment environment. KNN, if you don't have limitation of space, if you don't have limitation of time, KNN is very simple. It will be easy to operate. Okay, but Naive Bayes will be, that is the advantage disadvantage. Further, let me ask you, if you look at the different features, okay, does KNN have a problem with the features being correlated? Not really.
Not
Okay.
really.
Yeah. Does naive Bayes have a problem? Yes, it does. Because we have taken naive, right? The naive part of naive Bayes comes by multiplying these together. So here, what we are saying is the probability that someone has chills has nothing to do with the probability that they have a running nose. But we know in real life that is not true, right? There is some correlation between, if you're feeling cold and if you have a runny nose. They are very much correlated together, right?
Mm-hmm.
And does someone have a fever? Yes, so all these quantities are actually very correlated. So is fever and headache related? Yes, to some extent. Is runny nose and fever related? Yes, to some extent. Is someone feeling cold and having fever related? Yes. So there is interrelationship between the different features of this data set. And naive Bayes assumes that there is no interrelationship. That is why we are multiplying the probabilities together. Okay? Because of which naive Bayes may have a problem. So it may have a problem, especially when your data is correlated with each other. You have high correlation between your data, then naive Bayes may not give you a good solution. And KNN does not have that problem. Right? So both these algorithms, KNN and naive Bayes, they have certain advantages, certain disadvantages, depending upon what we are looking at. Okay. Of course, we can also use metrics like accuracy, precision, recall in identifying which algorithm will do better. Okay. But we should also consider other criteria. That is, how is my deploying environment? How much space do I have? How much time do I have? In how quickly do I need to give the answer? Okay. Further, does my data have correlation or not? So maybe my data on test set would give me good results for naive Bayes, but my final your deployment results may not be as good, and so on. Okay. So these are the questions that we need to ask ourselves when choosing which algorithm to choose. Okay, and going ahead with one algorithm. Okay, do you have any questions before we stop for today?
No, Elijah.
Okay, great.
It was good
So,
actually.
yeah, it's amazing. It's amazing, especially if you see how simple machine learning is. So this is nothing new actually. We have had Bayesian theorem from 70s or so. Okay, we are only finding new ways of incorporating that with data to use that to answer some probabilities, to answer some classification problems. In the next class, we'll look at decision tree classifier, and uh, along with decision tree classifier, we'll also look at random forest. Okay, or at least we'll get an idea of what is the background. So even for this, if I ask you to code this, it would not be very difficult to code this solution. Okay. Interestingly or luckily, we do not have to code this. We have very good libraries that we can directly use. But if we understand how they work in the background, that can help us later on in our data science journey when we have to choose between multiple algorithms. Okay. So
Okay.
with this, we'll stop for today, and we'll continue on Monday. I have one more thing to share probably. On Kaggle, I found there is an option to create your own competitions. Okay? So I have taken a data set called as heart disease dataset, and it is a private competition. So I will share the link with you guys, and maybe we have not reached to that level where you can directly participate, but I hope if you do some learning on your own, you could be able to participate on that platform. Okay, so try submitting some answers. If you have any questions, we can discuss in the WhatsApp group, or we can discuss in the next class. Okay, so once you have little hands-on practice, it will be interesting. So this competition is open to all the students that I'm teaching. So there are different batches also I'm teaching, and they will also participate in this competition. So it will be interesting to see how we can take things that we have already learned and apply it here and test, at least in a friendly environment, test with each other how good or bad we are doing, and then we can help each other out. Okay.
Yep.
Yeah, I will send the link in the group. See you guys on Monday. Bye bye.
Bye.